Welcome everyone. I am Jayanta Devnath, a second-year PhD student from the University of Iowa. This presentation is about our paper titled When TLS Meets Proxy on Mobile. This is a joint work with Professor Siu Shao from the Chinese University of Hong Kong and my advisor Professor Omar Choudhury. Let's begin this talk with an introduction to proxy-based mobile browsers. Google Play Store contains hundreds of proxy-based mobile browsers. In these browsers, traffic between the browser and remote website is forwarded through a proxy server to perform activities such as data compression, geo-blocking bypass, and censorship circumvention. In this study, we want to perform analysis on security implications of these browsers. Particularly, we want to evaluate how the proxy servers maintain the communication security when the traffic is secured by TLS or transport layer security. Over the last few years, several studies have been done to evaluate the security impact of HTTPS interception or TLS interception on different client-side software such as antivirus, parental control applications, as well as network appliances such as middle boxes. However, our study is different from this because we focused on a new domain called proxy-based mobile browsers, and uh, these browsers, other than TLS interception, rely on another class of connection establishment technique called HTTP tunneling, which was not considered for previous works. In addition, these mobile browsers don't get enough attention like the desktop browsers in case of enforcing security policies. These are the contributions of our paper. This is one of the first studies on security implications of proxy-based mobile browsers. We developed an automated experimental framework. Furthermore, we found security vulnerabilities in most of the browsers. This is the outline of this presentation. I have already talked about the motivation and contributions of this study. Now I will briefly discuss about some background information. Let's begin with TLS or Transport Layer Security. TLS is a widely used security protocol which provides confidentiality, integrity, and authentication between two entities exchanging data over the internet. For example, when we browse a website with a URL that starts with HTTP, all data is sent in plain text and a man-in-the-middle attacker can easily read the data. To solve this issue, HTTPS is used. Since HTTPS runs on top of TLS, traffic gets encrypted between the browser and remote website, and it solves the issue of confidentiality that I have mentioned. Now let's look at the messages exchanged in the general version of TLS protocol to establish a secure channel. Initially, client and server exchanges hello messages to negotiate security parameters such as TLS version, cipher algorithms, and so on. Server also sends a certificate chain to the browser so that the browser can validate the authenticity of the server by verifying the root certificate and other information on the certificate chain. When these two parties successfully complete exchanging rest of the TLS handshake messages, a secure channel is established between them. From now on, these two entities can securely exchange encrypted application data. Now the next question is, how do proxy servers in our case handle TLS protocol? So we have found the proxy-based mobile browsers rely on two classes of connection establishment. The first one is TLS interception and the second one is HTTP tunneling. In TLS interception, the proxy server breaks the end-to-end security guarantee provided by TLS. Whereas in HTTP tunneling, the proxy server creates a tunnel between the browser and the remote web server. In the next two slides, I will show you how these techniques work. In TLS interception, the proxy server places itself between the browser and the remote server. Whenever the browser receives a client hello message, the proxy intercepts the message and generates its own version of client hello message and sends it to the remote server. By continuing this process in both directions, the proxy server ends up establishing two TLS sessions, one with the browser, another with the remote server. Since the proxy has keys for both TLS sessions, it can decrypt any message exchanged between the browser and the remote server. The most tricky part here is that the proxy needs to install its root certificate to the browser to bypass validation of the proxy signed certificate. However, it's very trivial in this scenario since the browsers are usually shipped with the proxy's root certificate. In case of HTTP tunneling, browser sends a HTTP connect request to the proxy server to establish a tunnel with the remote server. The proxy server then tries to create a TCP connection with the remote server. If it is successful, proxy sends an OK message to the browser. Now the browser can start communicating with the remote server using a tunnel, and the proxy server simply forwards all subsequent TCP stream. Here only one TLS session is established between the browser and the remote server. Thus the proxy cannot decrypt any message. Now let's focus on the experiments and security evaluations. Our experimental setup consists of three major components: an Android device, an Apache web server, and a laptop with Wi-Fi hotspot. When a browser do not select proxy server automatically or don't have its data saving feature enabled by default, we manually select the proxy server or enable data saving feature from the settings. Now when we visit our Apache web server from this browser, all subsequent traffic passes through the browser's proxy server. To capture the traffic between the browser and the proxy server, we use Wireshark in the laptop. Similarly, we use Wireshark in remote server machine to capture traffic between the proxy server and Apache server. To select the representative browsers for our experiments, we consider the proxy-based browsers which have significant number of downloads in Play Store. Thus, we select 34 such browsers and capture traffic following the technique discussed in previous slide. Now we use this traffic file as inputs to a highly automated heuristic-based proxy server identification and classification algorithm to find out the proxy server address and classify the browsers. Finally, we find 16 TI browsers and 18 HT browsers from those 34 browsers. So details of that heuristic-based proxy server identification and classification algorithm is specified in section 3.3 of the paper. These are the browsers that we have considered for further security evaluations. Now, in case of TI browsers or TLS interception browsers, we want to evaluate whether the strength of TLS sessions on both sides of the proxy servers are equivalent or not. To determine the strength of the TLS session, we consider four factors: certificate parameters such as signature hash algorithm or RSA key size, TLS versions, cipher switch quality, and proxy server's certificate validation process. In addition, we also evaluate browser's behavior when the proxy server or remote server selects or presents a vulnerable certificate chain, a weak cipher suite, or weak TLS version to the browser. Now I will present some major findings from our security evaluations. We have seen that proxy servers of TI browsers do not maintain symmetry in TLS sessions. For example, the TLS session between browser and the proxy server uses fixed certificate parameters, TLS version, and cipher suite, ignoring the parameters exchanged in the TLS session between the proxy and remote server. This is a false sense of security, since a user from browser side cannot have any idea what is happening on the other side. So even if browser proxy TLS session is strong, proxy remote server TLS session can be significantly weaker. And this can downgrade the security of overall connection. In a later slide, I will show one such example from our findings. This is one of the interesting findings that we found for UPX browser, where its proxy signed certificate uses 1024 bits RSA public key, whereas NIST recommends usage of such short keys so NIST doesn't recommend usage of such short keys from few years ago. In addition, we found usage of weak or broken cipher algorithms of the browsers or proxy servers. We found all the browsers, including the proxy servers, are using weak and vulnerable triple-dash encryption and SHA-1 hash algorithm. We found 3 browsers using severely broken and deprecated RC4 encryption and MD5 hash algorithm. And it's sorry to say that in browser interface, no warning message is shown to user about these weak parameters. In our findings, UC Mini browser had the worst security policies during data saving. This browser has over 100 millions of downloads. However, its proxy server was using RC4 encryption and MD5 hash algorithm till 2019. Though this browser has removed their data saving feature from 2020 due to security issues, we found that their proxy servers are still operational to support the older versions of this app. In case of certificate validation, the browsers or the proxy servers are very lenient. When we fed different vulnerable certificate from our remote Apache server, most of these browsers or proxy servers fail to properly validate those certificate chains. For example, almost all the browsers or proxies fail to detect revoked certificates. And few browsers were also reluctant to check expiry date or common name of the certificate. We found 4 browsers that don't perform any certificate validation at all. All 34 browsers or proxy servers support weak TLS version 1 for backward compatibility. For that reason, users have the chance to get affected by beast or sloth attack. Most interestingly, proxy servers of UC Mini browser only support SSL version 3 and TLS version 1. So SSL version 3 is already deprecated few years ago due to severe security issues. On the other hand, by default, browser proxy TLS session for this browser uses TLS version 1.2, which is comparatively very strong. So this is actually a perfect example of false sense of security that I mentioned before. In summary, we evaluated 34 browsers for 1 year and found security issues such as leniency in certificate validation, asymmetry of TI browsers, usage of weak cipher suites, usage of certificate parameters, and usage of TLS version, weak TLS version. In one line, we found that TLS is severely downgraded in most of the proxy-based mobile browsers. For these reasons, we recommend the proxy servers and browsers to validate certificate chain properly. Check strength of certificate parameters, disable weak TLS versions and cipher suites, and block weak TLS sessions or at least show warning to the users. We reported our finding to all the vulnerable browser developers. However, we got reply from only 6 of them. 4 of them acknowledged our finding and promised to solve these issues in next updates. 2 of them rejected our recommendations due to backward compatibility issues. So this data actually shows how reluctant these app developers are regarding the security issues of their browsers. In summary, our study explored security implications of proxy-based mobile browsers. We developed a highly automated experimental framework. We also found security vulnerabilities in most of these browsers, and we reported our findings to the respective browser developers. And our source code for proxy browser identification and classification algorithm is publicly available. Thank you for your kind attention during this talk. Now I am happy to take any questions from you.